All right, welcome to the 10th EE2950 SI session. Today we're going to be looking at capacitors and inductors. This is going to be the next part in our course. So looking at capacitors, we have symbols and units. So our symbol for capacitors is going to be C. And our units for the capacitors is going to be farads. Okay, where the capacitor is going to be a flat plate and a curved plate, where the flat plate will be the positive, the curved plate will be the negative. And our current will enter through the positive terminal of the capacitor. All right, our base equation for the capacitor is going to be Q is equal to CV, which this just relates charge by multiplying the capacitance and the voltage. It's analogous to the Ohm's law, V is equal to IR. All right, and if we take a look at charging and discharging, so for capacitors have the ability to store energy and also to discharge it as well. So if we wanted to take a look at a capacitor, we can say that for charging, if we charge it up, time is equal to 0 and it's initially discharged, we can treat it as a regular wire. However, if we let time run to infinity and it's charging up, we're going to treat it as a clipped out wire. Okay, and where time goes to infinity, we consider this to be steady state. Another way we consider steady state is for 5 time constants. So that's another way of looking at it. Say if it's discharging. So if it's discharging, and it's initially fully charged, so time is equal to 0. It'll look like that. As time goes to infinity, it'll return to a wire. Okay, so moving on from here, if we go look at the combinations, so for a capacitor, we're going to flip the resistor rules, meaning that if they are in series, we have to do 1 over CS is going to be equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus ... And then if they are in parallel, we will just do C parallel is equal to C1 plus C2 plus C3 plus ... Okay, and we're going to see examples of charging and discharging later on in this SI session. So don't get concerned if that's not quite clear yet. All right, looking at inductors. So inductors are going to be denoted by L, and they will be coils. Our units for these are going to be henries. Henry, where we'll have a positive terminal, negative terminal, and the current will flow through the positive terminal as usual. There is no base equation that we have for these. If we jump down to the charging and discharging, so if we go to the charging, initially, if there's nothing going on with it, we're going to treat this like an open wire. But after a long time, as time goes to infinity, we'll treat it as a regular wire. And we'll notice that it's just the opposite of the capacitance. Reason being is that the capacitance stores and then the charging resists. Okay. So the inductance resists current flow. All right. So if we initially have current coming through this coil, it's going to take a long time to pass through, and it acts like it's resisting the flow of the current. But after a long period of time, you'll make it through to the other side, and you'll continue on with your current flow. Okay. And then, of course, just once again, this is modeled as steady state, which is also considered to be 5 tau. And then discharging, it's just going to be the opposite of what we had before. So if you can remember one, you can remember the others. It just takes a long time. It just takes a long time for these things to change how they interact in the circuit. Looking at the combination, we're going to keep resistor rules. So for series, L series will just be L1 plus L2 plus L3 plus ... And then for parallel, it will be 1 over LP is equal to 1 over L1 plus 1 over L2 plus 1 over L3 plus ... All right. And that looks like it'll do it for the concepts. I will see you in the problems.